This conference will now be recorded.
Well, since I hope everyone is here and we have a lot to cover, we really should begin today's virtual conference. I really appreciate you all for attending today's virtual conference on Internet 8th European Congress on 3D Printing and Additive Manufacturing. So, a very good morning, good afternoon, or good evening to one and all present here virtually with me today. Let me introduce myself. My name is Clara McBroom, Conference Secretary at Coalesce Research Group LLC, and I will be available for any of your queries or questions throughout the webinar to help you out technically and organize the webinar successfully. For the next 5 minutes, please allow me to give a brief description about our organization, Coalesce Research Group, and also the further instructions. Coalesce Research Group LLC is very delighted to welcome you all for the speakers, supporting association, students, and delegates present here virtually with us today. With the aim mark the scientific excellence by facilitating conversation, sharing knowledge, Coalesce Research Group follows through the objectives of setting standards in delivering excellence in the research among the researchers and industries. Promulgating the research through conducting events and online webinars from various fields of science, especially from the stream of medicine, science, and engineering and technology. Within a short duration, we have succeeded in creating a platform for developing a strong professional network with the people across the world from their respective fields that they haven't connected in a while. As a global scientific event organizer, we plan and carry out international conferences, meetings, seminars, symposium, and workshops, providing the best delegate experience, excellent networking opportunities, conversation leading to innovation, learning new opportunities. Just recently, we have also started our own platform for open access peer reviewed scholarly literature where all the content is freely available without any charge to the readers. As being the very new to journals, we have coined up some interesting journals and we have also formed the editorial board. And we will be very glad if any of our today's attendees, the speakers, students, or delegates would extend your support by clicking the journals and will be interested in publishing an inaugural issue at any of the journals according to the area of expertise. Finally, I would like to thank all the attendees and participants of today's virtual conference on 8th European Congress on 3D printing and additive manufacturing, and I hope you enjoy the webinar and gain the knowledge from the sessions today. We also hope your participation will contribute to new research findings and that will lead to new collaborations and research initiatives. Before we start with the session, I guess some of you will be new to GoToMeetings app. Let me just explain you the important tools required for the presentation. On the GoToMeetings app or a web page, you can find four icons at the bottom center: mic, camera, screen, and end button. The mic button, click on that to mute or unmute yourself. I request you all to stay muted while our speakers are presenting their research work so that it does not cause any disturbance to them. Camera button, you can use this button to share or unshare the web camera. If you have the option to share the web camera, you can do it and it's completely your choice. The screen button, you can use this button to share your screen. This is the main part. During your presentation, after I call your name from my side, I will be making you as a presenter and will give you the permission to share your screen. Then only you can able to share your screen. So once I make you the presenter, you can click on the screen button and you will find a pop-up window to share your screen. This Then the last one is the end button. This is the fourth icon where you can use this to lay the session. On the top center, you can use the options to change your display settings. At the top right corner, you will have three icons: people, chat, and settings. In the chat option, you can chat with me or with any other participants. For the settings, you can use this button to check for the settings for your mic, speakers and microphone. So as I mentioned, kindly remain muted during the presentation so that the presenters does not get disturbed. And for any questions, you can ask the questions or you can send your questions in the message box too. Well, let's not take much of your time. Finally, I would like to request you all to please give us a brief introduction about yourself before starting with the session so that we can know about you virtually. And now let's move into our session. The first presenter is Dr. Hamid Mehrabi from University of Sutherland, UK. Now, Dr. Hamid, are you ready with the presentation?
Yes, I am. Thank you.
Okay, Doctor. Now I'm making you as a presenter. Kindly click on the screen button to share your screen, please.
Okay. Can you see my screen now?
Yeah, your screen is visible. Can you make it as a presentation mode and start your presentation, please? Yeah,
I'm
perfect. You can
sorry?
start.
Yes.
Yeah, perfect. You can
Okay.
start.
Okay. Well, good morning, everyone. My name is, as Carl said, my name is Hamid Mehrabi. I'm associate professor at Sunderland University, uh, lead for Advanced Manufacturing Group, Faculty of Technology, University of Sunderland. And the talk today is additive manufacturing versus traditional manufacturing processes. Mark Armstrong is my PhD student. Nida Navid, she's presenting a paper in Amsterdam. She's one of my colleagues, senior lecturer at the university. We working with on additive manufacturing at the School of Excellence of Additive Manufacturing, Center of Excellence. And the picture you see is the university, the beautiful place that we work in, Sunderland University, next to Port of Sunderland, and at the background is the North Sea, the other side of Amsterdam. I mean, you are the other side in Europe, you are just opposite side. Well, we are more parallel to Denmark. Anyway, so that's me. We work for, we try to uh, understand more about additive manufacturing, its metals and polymers and ceramics. And that's why I was going to share what I know in this PowerPoint, in this presentation. Well, to start with, anything we talk about right now these days is global warming, net zero, environmental sustainability, and zero waste. Well, I learned about, I mean, my talk is my a little bit of background for last, let's say, 20 years. Uh, the data that I was collected, and this presentation is based on many years of research and different manufacturing processes. But the main idea came to our mind, my mind, zero waste 15 years ago, when I learned that we are talking about productivity all the time, reduce scraps all the time, improve profit, but without considering the environment. And I learned about zero waste. Then I realized zero waste is very, very difficult to achieve. Then more uh, realistically, environmental sustainability came across, and then now net zero. All of these for avoiding global warming. We're trying to reduce CO2 emission as much as we can by reducing energy consumption as much as we can, and that is why I actually start comparing additive manufacturing with old technology or traditional technology. And to be able to compare, we do need to go life cycle analysis. We need to check well to wheel. I had an experience in 2015. Some companies came to us and they said, sand casting companies producing engine blocks made of made of cast iron. They argued that the aluminum engines are, we keep saying that there are less polluting parts, which is true because of lightweighting, but we should look at it well to wheel from the beginning to the end to see how much energy it's consumed and how much pollution is created from extraction of aluminium and to the end life of the automobile. So when we did the research, we had 7 MSc students starting doing this research from all over the world, and we came across that yes, aluminium consumes more energy well to wheel and creates more pollution than cast iron. So that was one approach. But now, I mean, we say we've been teaching aluminium. We were talking about lightweighting of aluminium for such a long time, but without considering the life cycle analysis. So what we did, we start. Well, part of my work was I've been working on traditional manufacturing processes like casting, sand casting, die casting, high pressure die casting, low pressure die casting, investment casting, centrifugal casting, forging. Well, I haven't been working on all of them, but what I'm saying that traditional manufacturing processes, these are the traditional ones, and there are so many more that I can't recall now. But forging, hot or cold, powder metallurgy, injection molding of polymers, metals, ceramics, extrusion of both metals and polymers, machining, turning, milling, boring, drilling. These are the primary processes. And after doing this, we might need secondary processes like heat treatment. My PhD is heat treatment, machining, welding, and assembly. My MSc is in welding, 1989. Heat treatment, 1993. My supervisor, Professor Barry Means, he was my supervisor for my PhD, heat treatment, and he said, Hamid, nobody wants you. Why? Because they want to avoid heat treatment as much as they can. Why? Because it's an energy consuming process. That was 1993. So, to be honest, look at the life cycle analysis. Sand casting, and the head of Casting Federation, World Casting Federation, in a conference in Paris in 2014, he mentioned that casting is forever. No matter what, we do need shaping the materials, and casting, nothing can replace casting. And in a way, he is right. Sand casting, which is the simplest and oldest technology, when you look at the life cycle through well to wheel, you will see such a long process, as you can see on the map. This is done by Mark, my PhD student, and I asked him to do a well to wheel or life cycle analysis of sand casting, and he came up with this diagram, which is very clever. As you can see, the energy consumption on the top left, material production, and if and then sand production creates you need to create to extract sand and process it creates requires a lot of energy and creates a lot of CO2 emission. Material itself, the metal itself, needs extraction and processing and shaping it for the raw material, and then to go through the process of melting, core making, and mold making, making the mold, and after doing this, again melting, uh, melting and uh, casting, pouring the metal in casting, solidification, shakeout, fettling, machining, and heat treatment, and so on. So you can see was such a long process of for a very simple manufacturing process, casting, sand casting, very old technology. But look, so much materials, so many processes, so many energy, and so much CO2 pollution. And again, that's sand casting. Die casting for producing aluminium parts. Die casting uh, again follows such a long process. This is only in the foundry sector. Drawing, tooling, and tool making and casting, and carry on doing the same. So this is a die casting process. And machinery for high pressure die casting. For high pressure die casting, we use different size of machinery. A smaller size, smaller parts and components, you need a smaller machine. For bigger machines, for bigger parts and components, higher and bigger machines are used. And I tell you, for example, there are companies uh, in different parts of the world producing engine blocks, 3-cylinder, 4-cylinder engine blocks made of aluminium, 300,000 to 400,000 per year using these machines. So you can see the speed and the size of the bigger the components and the parts to be produced, the bigger the machines. And that was die casting. Another, I deal with the casting processes, and this is my expertise. I've been working on investment casting for a long time, and produced the know-how for making ceramic shell mold and injection and ceramic cores. I'm going to make something out of this. So investment casting process, as you can see, is a long process again, making the mold, producing the pattern, uh, making the mold for injection molding, and produce the wax pattern by injecting the wax into the mold, making the pattern assembly, and using the coating the assembly in a slurry, in a ceramic slurry, and stuccoing the slurry. I'll show you in more detail in a minute, and making the mold, dewaxing the mold, and firing the mold, and pour the metal into the mold and breaking and get the final product. That is investment casting. I said it in 30 seconds, but it's really to make the ceramic shell mold for any product. You need 1 week to make the mold. And again, to be more familiar with the process, is making a mold here, a mold, and as you can see, injecting the wax pattern, produce the pattern, and well, they say group number welding, sticking the patterns together, produce the ceramic, as you can see, and dewaxing it, firing it, and ready for pouring, and finishing, cutting, and inspection, and machining, final machining, and packaging. So you can see what the long process investment casting and time consuming is, and what the high energy consumption all these casting processes, very high energy consumption. As you can see, when you think of casting, you see this sort of heat and this sort of melting, this sort of melted material pouring into these semi-automated sand casting, and this is the manual casting. As you can see, people are involved pouring the molten metal into the sand ball. A very, very old technology, but still so many applications cannot be replaced by any other method. So what's the point of talking about this? So what we did, the point that I'm trying to make, 2015, 16, 17, we did a project on energy foundries. How much foundries consume energy, how much energy foundries consume. And we visited quite a few foundries in Europe and in England, in the UK, and we collected data from 12 foundries, energy consumption, and there were sand casting foundries, aluminium sand, cast iron sand casting, investment casting foundries, different die casting, aluminium die casting foundries, and batch production, automated production. So these variation, you can see the variation of their kilowatt per ton, how much they consume per ton of casting. F1, Foundry 1, which is an aluminium sand casting foundry, batch production, consumes around about 15,000 kilowatt per ton. Whereas F12, right at the end on the right hand side here, F12 consuming 2,200 something kilowatt per ton, as you can see. And we came up, and this one is sand casting batch production. The F12 is sand casting cast iron, and this is F1 is sand casting aluminium batch production. F12 is sand casting cast iron batch production. So you can see aluminium, which is lower melting point, is consuming more energy than cast iron, which is much higher melting point, 1250 above, aluminium 700, around about 700 degrees centigrade. And a lot of people were arguing that how can you compare all this? I said how we can compare, we calculated SEC, specific energy consumption. What is SEC? SEC is, this is annual energy consumption of all these foundries, annual in a year. We collected all the energy consumed in a year divided by tonnage produced. So we call it kilowatt per ton. So energy a foundry consumed all through the year, for not just for melting, for the whole lighting, for welding, for heat treatment, everything that they can do, and the overall energy consumption divided by overall tonnage produced. And we call it SEC, and we came up with this figure, which worked out well. Why? Because this is a very good way of actually benchmarking the foundries. And using the information we collected from F8, Foundry 8, which was a fully automated aluminium foundry, producing, as I said, 300,000 to 400,000 engine blocks, 3-cylinder, 4-cylinder engine blocks by high pressure die casting, 24/7. We learned that automation, rate of automation, and speed of production, and less less downtime, which it can increase, it can reduce the kilowatt per ton. So the more you produce during the day or during the week or during the month will break down your kilowatt per ton or sake. In other words, it increases your efficiency. So F12 and F11 and F10 were much more efficient than F1, F2, F3. And based on what we learned from F10, 11, and 12, we helped F1, F2, and F3 to improve their process, reduce their energy consumption, reduce their sake. And this is why I'm telling you all this. What's got to do with the additive manufacturing? It's to do with energy consumption in additive manufacturing. When I came up with this data 2015, 16, 17, and I had it in my mind, I joined Sunderland University to do some research, SAM project, to do some research for supporting SMEs, small manufacturing enterprises in the Northeast. And I learned quite a lot about additive manufacturing, because part of the work that we were doing supporting the SMEs was provide them with information about additive manufacturing, how they can benefit from additive manufacturing. And while we were doing this, I started to learn more about metal additive manufacturing and compare metal additive manufacturing with traditional manufacturing processes based on energy consumption, because that was one of the issues in terms of sustainability, in terms of net zero, that is all in all of our minds. So based on this information that we collected, based on the auditing that we did and the data that we collected from foundries, we came up with 10 rules, which is on public. It's going to be published fairly soon. These 10 rules: energy management, energy audit, product design, training, efficient melting, increase yield, maximum capacity, rate of production, maintenance, and reduce process steps. Again, from these, when we talk about Industry 4 and Industry 5, going towards Industry 4 and Industry 5, maximum capacity, rate of production, and reduce process steps somehow is related to additive manufacturing. I'll tell you why. And increase yield and yield as well. So I explain how this can be related. Anyway, that is about traditional manufacturing processes. Now, talking about additive manufacturing processes. As you all know, AM of plastic, of polymers, stereolithography is one way of doing it. Fuse deposition modeling, binder jetting, these are for mostly plastics. AM of metals, powder bed fusion, which in this work, my work is basically I'm comparing casting with powder bed fusion, direct energy deposition, and maybe some direct and binder jetting and liquid drop printing. Well, and there are more that, as you know, AM, advanced additive manufacturing, 3D printing is advancing so rapidly, and we cannot catch up. No matter how fast, how up to date we are, something happens on a daily basis. So, which is interesting as well. But if we compare what I showed you to begin with, sand casting, the life cycle analysis of sand casting, and life cycle analysis for 3D printing or powder bed fusion, you can see only few sections: mining, metal processing, feedstock, printing, post-processing, and recycling, and going back to the circle. And again, metal additive manufacturing, MAM, process workflow, design, build, stress relief, support removal, finishing, heat treatment, inspection, handover. So with what I showed you in terms of sand casting, or die casting, and investment casting, now look at additive manufacturing. This is our center of excellence for additive manufacturing. We just establishing this new place, center in at the Faculty of Technology, St. Peter's campus, and I took this picture while they were working and preparing the place. So that's why you can see the wires. These are not there anymore. But anyway, compare the old technology, sand, dye, and investment casting. Look at this, how tidy, clean, and small spaces. Mind you, we do have bigger machines now. These are one is inkjetting, one is the one. This one is FDM for polymers, and this is for carbon fiber FDM as well. So you can see how tidy suddenly manufacturing process became as compared with what I showed you earlier. How tidy, how organized, we can actually produce parts on the carpet. And this is, I call it the magic of making metallic parts, a simple FDM. They call it atomic diffusion additive manufacturing. This is what we have at this is our metal printer at Sunderland, at our Center of Excellence. Metal printer by ADAM, which is very, very clever of producing metal parts at room temperature. Very low melting temperature. It's just that you simply printing the, if I show you here, a typical extrusion, the filament or the binder, the filament here is normal polymer with a metal powder inside. With the particles of metals inside the filament, we just produce the part, produce the metal part using the same extrusion process like we do it for FDM. This is FDM process. And when the part is finished and completed, we get rid of the binder. The process called wash off. We wash the binder off, and then we sinter we put the green part in the furnace and sinter it, which is a very clever way of doing it. Altogether, it's printing can happen at room temperature, but we do need a furnace to actually sinter the final part. So another process of binder jetting, these are Mark's drawing. I show off with his drawing. He's very good in SolidWorks, and he can draw anything with it. Look, he drew a binder jetting machine, and as you can see, very compact process. It can be small and big, depending on the size. But again, and with the powder bed fusion, very compact and very tidy process. I show you more machinery as well. And again, with another one, which is a typical direct energy deposition machine, or DED we call it. This is again another additive manufacturing process for metals. But what I want to show you, this is DED, fusion mechanism with melt pool and heat effector zone. What I wanted to show you, this picture, this photo, it reminds you of, I assure you, if any of you are involved with welding, as soon as you see this picture, it reminds you of welding. And that's why I become involved so much with additive manufacturing, especially with metals, because of my background, which as a metallurgist, as a somebody who deals with casting and welding and heat treatment. And look, everything you do with metal additive manufacturing is very, very similar to what we previously been doing. So there are so many common factors involved here. As you can see, DED, here we're dealing with powder, but DED we do work with wire as well. They call it DED wire. Uh, they call it direct energy deposition, but instead of using the powder, we use the wire, which is exactly like TIG welding. With TIG welding, we use a filler wire as a filler, and we melt it with a very high with high heat input using a tungsten electrode, and or laser welding as well. Very similar, and it creates a melt pool. Here we got powder, but over there we got solid metal which is melted. But again, process of heat input, solidification, and the defects created in the process very, very similar. That is why I can, if I've got some knowledge of different type of defects in welding or casting, I can actually deal with this process much easier as well. With powder bed fusion, with DED, with any sort of metal additive manufacturing, which is involved with melting. So these are the common factors between traditional and additive manufacturing processes. Oh yeah. Now, again, we did some energy measurement and some energy calculations and compared with energy consumption of foundries. And I just added the three DMLS. This is DED, the first one. This is energy consumption by DED. This is energy consumption by ADAM, the machine that I showed you that we've got at Sunderland, and PBF, powder bed fusion, or SLM or SLS. As you can see, these machines are much higher. These processes consume a lot more energy than foundries per part, per kilogram, or per ton. Per part, per kilogram, per ton. As you can see, I actually, this is the same graph, this is the same chart, but that I showed you at the top, but I added these three six or these three lines into the same chart. As you can see, the F1, which is the worst case scenario in foundries, if I go back to the diagram, this is F1, if you remember, F2, F3. So in comparison with energy consumption of PBF, powder bed fusion, ADAM that I told you is a magic printing metal room temperature, then we sinter it, and DED, what I just showed you earlier, direct energy deposition modeling. So you can see how much energy per part, per kilogram they consume. We're talking about something 95,000 kilowatt per ton for DED, ADAM 70, let's say 70,000, and PBF around about 18,000, much more, 18,000 kilowatt per ton, much more than F1, which is the worst case scenario in sand casting foundries. This was very interesting because a lot of people talk about efficiency, talk about net zero, and one way of achieving net zero is going towards additive manufacturing, but it's well, we have to look at it a different way. I'll show you. tell you something later. Yeah, my other PhD student, Wu from in Japan, she was working on additive manufacturing of plastics, additive manufacturing of recycling plastics, and uh, she did. This is based on her work, and she was comparing injection molding of plastics with SLA and FDM, and these results, based on her work, showing that printing plastics is again is more energy consuming per part than injection molding or even SLA. And why? Because yes, because injection molding and investment casting, as I mentioned at the top here, one reason of improving efficiency is rate of production and reduce steps, so rate of production and maximum capacity. So the reason that companies can improve their efficiency, energy efficiency, is by uh, producing more fast and divide the energy consumption by tonnage produced, which with additive manufacturing, it cannot be done as good. Why? Because it's a slow process. So this is one of the things that I wanted to share. Specific energy consumption for plastics and for metals. In terms of energy consumption, additive manufacturing is not there yet. But the reason that we can Wu's PhD came up with localization. Wu's PhD was talking about plastic additive manufacturing of additive manufacturing of recycled plastics, and she came up with the end result that if additive manufacturing used accordingly and following the standards and locally, we can reduce, and by if additive manufacturing is used locally by consuming, by reducing the well, let's say we call it local additive manufacturing. Local additive manufacturing. If we use it locally and produce parts locally, we can reduce transportation. By reducing the transportation, energy consumption is reduced, CO2 pollution by transportation is reduced. That's another way additive manufacturing can help if we produce parts locally. And not only that, it actually avoids immigration. It creates jobs locally, and people stay put, and they don't travel, they don't immigrate, and they stay in rural areas and actually start doing their own thing. Anyway, this was part of the theory that she came up with, and uh, and she came up with some calculation that we could save 20% of energy produced by transportation if recycling and additive manufacturing of plastics can be done locally. Anyway, that was part. And to make the story short, because I'm getting too long, that was one advantage or one discussion between traditional manufacturing and additive manufacturing in terms of energy. But I wanted to share something else with you. I've been working on hollow gas turbine blade, trying to improve the performance of the gas turbine blade, improve the creep resistance, and performance and quality of the blade. So how there's more about heat sink as well, but I cut it short to gas turbine for the time being. How do you make gas turbine blade, hollow gas turbine blade? Gas turbine blade is made by investment casting. Wax pattern. For each blade that we want to make, we need a wax pattern. The wax is injected into a mold by injection molding of plastics So the wax is injected into a mold, and we produce a wax pattern for each blade that we want to make. And then we put it as an assembly on a tree, we call it tree assembly, and then is ready for dipping into the slurry. This is the process of making ceramic shell for gas turbine. So we put the assembly into the slurry few times, and then after wetting the assembly with the wax pattern with the slurry, after drippage, we there's another process called the stuccoing. We put more dry ceramics on top of that wetted pattern. And after doing this, we repeat after that, we dry it. In the controlled atmosphere, temperature, humidity, we dry the assembly. After 2-3 hours, we repeat this process again and again 6 to 7 to 8 times to get to the required thickness. And when the required thickness is achieved, 24 to 48 hours it's left to dry. After drying 48 hours, so we're talking about almost 2-3 days now. And after 2-3 days, we get rid of the wax. But in a process called autoclave, in a machine called autoclave, we get rid of the wax. The wax and we can reuse the wax for some other applications. So we can recycle the wax as well, but we get rid of the wax, and after the dewaxing, we fire the mold. We put it in the furnace, heat up to 950 to 1000 degrees centigrade to improve the strength of the ceramic shell and get rid of the extra waxes which is left in the body. And then when the part is ready, we start to cast. Well, when we say start to cast, this is air casting. For hollow for blades, we use VIM, vacuum induction, we have to cast it in vacuum. So you can see what the expensive process, what the timely process, what the time-consuming process this investment casting is. This is not for making a hollow blade. This is for making a solid blade. If you want to make a hollow blade, you need a ceramic core. Before printing the pattern, we make a ceramic core by injection molding. We make a ceramic core, and then ceramic core is placed in the die, and then we inject the wax on top of the ceramic core. So we end up with a pattern with the ceramic cores inside. So as you can see, the ceramic core inside the pattern. Now we do the same process. Same process. The ceramic shell is ready. Ceramic shell is ready, and the part is cast, and we break the ceramic, and then we have to break the ceramic core inside the blade and come up with hollow blades. So you can see what a long process. Injection molding of ceramic, and then making the ceramic shell to produce these blades. Now Siemens, this is a power bed fusion printer. I just picked it up from internet. But now Siemens has argued that they made the hollow blades directly in the machine. Can you imagine the process that I explained? Two different and big spaces required, big furnaces required, high temperature furnaces required, so many steps for drying room for ceramic shells and all that. Now they can make that blade directly from a Cat 5 using a powder bed fusion, using a machine in a small room. Yes, but and we did some tests. We ordered some investment casting. Well, we worked with an investment casting company in the UK, and they provided us with some samples, tensile samples, and we did some tests on their samples. 49494 is the ultimate tensile strength, and the yield 283. And our samples for ADAM samples that we produced, we came up with these results. Oops. We came up with these results. So in a way, and the CES EduPack software shows that we are in the right range, 480 to 635, the UTS megapascal, and the yield of 275 to 365. Shows that we are in the right place. I mean, ADAM and investment casting, they actually can work well in terms of strength of the material. It does the job. But there again, can you see the difference? But gas turbine producing by this machine, very slow. With what I showed you, yes, this is a very slow process, but you can make the melt when you make the ceramic shell in mass, then you can cast them in mass, and then again speed up the process. So as you can see, and one more, no matter what, investment casting of blades by directionally solidified structure and single crystal steel, it has to be we have to have a proper setup to be able to produce single crystal or directionally solidified structure, which cannot be printed by any machines yet, making it single crystal. So as you can see, there are so many differences, variation between these traditional and additive manufacturing, that what I've learned, I try to educate the companies. I try to um, let them know that yes, you don't need to replace your process by additive manufacturing, but an additive manufacturing machine or additive manufacturing, it's very, very helpful to have in your workplace, as we call it. So additive manufacturing, conclusion to make it short, and additive manufacturing AM and traditional manufacturing TM processes are two distinct approaches to creating parts and products. Each method has its own strengths and weaknesses, making them suitable for different applications. Ultimately, the choice between additive manufacturing and conventional manufacturing processes depends on factors like design for the complexity, production volume, material requirements, lead time, cost consideration, and desired end-use properties. And the final one, in many cases, this is my conclusion, a combination of both methods, known as hybrid manufacturing, can be used to leverage the advantages of each approach. Thank you. I hope I didn't give you a headache. Any questions?
Thank you, Dr. Hamid, for your keynote presentation. Does anyone having any queries? I hope there are no queries. Once again, thank you, Dr. Hamid, for the presence and presentation.
Thank you. Thank you. Thank you for your time.
Now, thank you, Doctor. Now, let's move on to our overall presentations. The first oral presentation is from Dr. M. Irfan Hussain from University of Science and Technology, Wing, China. Hello, Dr. Irfan Hussain. Are you ready with your presentation?
Yes, thank you. I'm ready for two presentation.
Okay, now I'm making you as a presenter. Kindly click on the screen button to share your screen, please.
So
Yeah, your screen is shared. Kindly, please do
now
open.
is
Your
shared.
screen is with. Yeah, it is shared. Please make it in a presentation mode and start your presentation.
Okay. Now is it okay? Have you here see my presentation?
Your presentation is okay. Can you make it is in
All
a
right.
presentation mode so that we can see your change slides?
All right.
No, sorry. Can you, the bottom, you have a presentation symbol or in a slideshow? You can begin the slideshow. Yeah, there. Yes. It's perfect. You can start your presentation now.
It's okay. Welcome to. Uh, is it okay? Have you hear my sound?
Yes, it's perfect. You can start your
Okay. Okay.
presentation.
Okay. Hello, everyone. Welcome to my talk. I'm Irfan Hussain, PhD student. So today I'm going to talk about the DLP 3D printing of oxide ceramics. So here I will discuss about the printing of oxide ceramics, alumina, zirconia, 3Y Euretia stabilized zirconia, and kaolin printing, and also discuss about the optimization of slurry and sintering process. So here is my brief introduction. I'm working on the Department of Material Science and Engineering, University of Science and Technology, Beijing. So here in the last year, we have good ceramic powder metallurgy labs. I'm working on DLP. So in my group, we are working on different directions, simulation, processing, characterization. I'm working on the additive manufacturing process. So here is the brief introduction, the application of ceramics for they will use in the case of aerospace. They use tiles and nozzles, and especially DLP 3D printing have revolutionary in the medicines, and in case of semiconductor and the energy application. So here is the state of the art of my PhD research work. So the production of densified and defect-free ceramics and it is composite with the DLP process is currently difficult. The DLP process was mostly used alumina, zirconia, but a lot of improvement have been last 3 years. But in case of pure ceramic, can't meet the functional and the structural complexity due to the single phase of composition. And also one challenge about the ceramics used for in structural and functional system. So cause of the brittle of ceramics cause failure. So it need for tough and mechanically reliable ceramics. So here we can have a design concept to overcome this one. Firstly, we can alternating the ceramics layer with the different geometry, and secondly by tailoring the microstructure. So in case of additive manufacturing, I am using to printing by layer printing to overcome this issue. And secondly, the question addressed will be the influence of a sintering temperature and the correlation between printing direction and testing direction. So here is my specific objective of my research. So firstly, alumina reinforced zirconia in a suspension for high strength 3D printings. Secondly, preparation of homemade resin in order to overcome the printing and debinding issues. So third, measure the strength of DLP printed specimen with different influence distribution. And after investigate the compatibility and improve the microstructure, explore potential application for alumina reinforced zirconia composite for dental implants and triply period minimal surface pore structure and optimization of the process of debinding and sintering process. So here is the brief introduction of the digital light processing printing. So in case of digital, we are the basic building blocks of the resin, the monomers, oligomers, photoinitiator, and the UV blocks. So the build here, if you see from the right side to bottom, here is how the DLP printing is working. So the first build plate moves to liquid resin and the DLP project image bed tray, and meat resin material solidify platform lift and layer separated from tray. The process is continually until the solidified. So here is the workflow of the processing. So firstly, the requirement of DLP. Firstly, the STL file we are using, the suspension we are printing, then the green parts are additive manufactured. Third is the debinding is the most crucial step where we need to remove the organic binder. And third is the sintering to strengthen the ceramics material. And finally, the final printed part we are printing. So printing parameter also in case of suspension is the most viscosity and high solo loading effects. So here is the background of the alumina reinforced zirconia. So in the composite material, they have customized properties because as mentioned before, pure alumina and zirconia have a single phase. So it is not meet the functional property. So for enhance the strengthening, I'm interested to reinforce zirconia. So in the right side is the image how DLP print. For example, the layers the build blade can move and the UV light cure the lights and the characteristic properties we need debinding and shift to the muffle furnace for strengthening and end user project. So here are the some common defect in DLP 3D printing or ceramics we are facing. The first one is the pores, because in case of when we prepare the slurry suspension, they have some oxide. So for oxide, we must need to remove. They create some bubbles during printing, so they cause the pores, and they due to the slice thickness. The second, as I mentioned, debinding to not completely remove the organics, so they cause some cracks, and if the not control the sintering process, the big cause of the cracks. And the high strength solid loading cause the lack of fusion, and some high temperature of the ceramics we are facing the brittles, surface roughness, fracture toughness, and the high temperature we are facing the linear shrinkage. So these are the big challenge. So control of the structure properties and defect, we are split into the structure. We can make the grain size, can control the properties. In case of properties, porosity, drastic decrease in grain growth, and some like as mentioned before, cracks are the big issue. From the literature, grain orientation in the texture alumina ceramics, we are can overcome this issue, demonstrate the ability to manufacture ceramics, achieve full density after sintering, and the fracture toughness green part with changing properties. And you can see in the right, we have some, after printing, they have some pores. So introduce the grain boundary phase to promote the toughing mechanism. Here is the novel material and advanced mechanism are key, because in case of state of the art material, we can overcome by using the microstructure properties and the benchmark performance by using the photopolymerization, because in photopolymerization they are monomers, cross linkers, light absorber, and the resin can control about this, the invoke advanced defeat mechanism, how the UV light infect, and thus because the most like a penetration issue if the solid content are high. So strategies for improving the strength of 3D printing ceramics, highlighting the novel strategy for improving the flexural strength parameter. So strategies, what have we reached so far? So the best is the optimal sintering condition to overcome homogeneous microstructures, influence the printing direction along x-axis, y-axis, and the z-axis we can print.
Hello, Dr. Irfan Hussain. Sorry for the interruption.
Okay,
Actually, your video is not being shared. I mean, the PPT presentation is not being shared. Can you,
really?
yeah, can you please check that?
Uh, I, I don't know. It's not sure.
We're going now.
I'm
We're
so
going now. बोल दे, what, what I'm about to. Can you please go to this app and reshare again?
Now is it okay?
Yeah, it is visible now.
Is now or
Yeah, kindly make it a full screen. Yeah, it's perfect.
okay. So
Continue with
the
your presentation.
Oh, okay. Strategies for improving the strength I have mentioned before. So here is the motivation of our research. If we can overcome this problem, first is the photo curing mechanism. Here, in case of photo curing mechanism, the reaction exposure and parameter affecting printing. So in case of, as mentioned before, oligomers and photo initiator primer and polymer, they can build with the under the UV light. So here is the reinforced zirconia we can use for enhance the mechanical property and densification in case of higher fracture toughness, higher flexural strength. In the case of green body, we using a DLP machine. We have three slice thickness, 25 micrometer, 50 micrometer, and 100 micrometer. And the process meter of the exposure time we can adjust with according to suitable. And the slurry suspension. The third is the temperature, like sintering, where is debinding, we can perform argon, nitrogen, and after sintering into the air, and the holding time can enhance the mechanical. So here is the novel approach to flexural strength. I have split into the four sections. The first is the powder of alumina reinforce, how it we can manufacture. Firstly, we take a two powder which observe the particle size, and then the mixing with ethanol, and then after ball milling we use the resin, make a slurry suspension, solar loading, viscosity, and after the second is the DLP process parameter. In case of DLP process parameter, we have a slice geometry. In slice geometry we have 25 micrometer, 50 and 100. We first check the base layer, and then we adjust the exposure intensity. So exposure intensity from 10 to 30 meter watt centimeter square, and exposure time start from 4 second to 12 second. After the third is the thermal process pyrolysis, where we need to remove the debinding and sintering. So we prefer to debinding under the argon to remove the cracks, and sintering under air to strengthen. And third is the strengthen the mechanical property by change the control sintering, high solid content, and strength hardness. So here is the whole flow chart of how can we enhance the mechanical property and cracks densify. So here in the right side is the curing thickness. This is the first step in the DLP process parameter, where we are using light intensity, exposure time, and the left side is the additive sintering. If we add small content of additive sintering like the magnesium oxide to control the microstructure, add the silica, zirconia, they add strengthen the material, and silicon carbide hardness reduce and reduce the shrinkage, and add of others like titania to enhance the strength. And the debinding process, as mentioned before, we perform argon atmosphere, then we shrinkage control XY, and the viscosity is the most important rheological behavior which ensure the printing of the high solid content. So the reason in the literature are using the photo initiator preferred with the DLP, TPO, BAPO, and all of other market they are used for. So I prefer to the monomers in my research is the 1,6-hexane diol diacrylate acid, because they are the high reactivity interpret of the photoinitiator. So second is the radicals ethylene glide called trimethylate, lower photopolymerization I have prefer increased, because the PEG 200 increase the viscosity, slow down the reaction, and increase the photopolymerized mass. So the resin first selection, as mentioned, HDDA, high reactivity and low viscosity. Then I prefer in my research TGDA for high reactivity and average viscosity. And the PEG polyethylene glycol 200 slows down the photopolymerization, printable suspension, low viscosity, high reactivity, and solid photopolymerized. So here is the chemistry of the coating industry in the DLP process. Here is the parameter as mentioned before, all of the curing depth, curing width, penetration depth, exposure light, UV light, slurry thickness, monomers, oligomers, and photo initiator. So after we are printing the different solid loading, here is the too low viscosity, ideal viscosity, and too high viscosity. If the high viscosity, the printing is very hard. So we can control by the monomers. So here is the research method after we are printing. First, we need to CAD file, translation the surface STL file, slice, and DLP printing. And the most important in case of we are the particle size and the shape of the powder, small size to ensure the smooth, spherical, and compatibility. Viscosity is the second step, is the rheological low viscosity to ensure the smooth surface, and UV curing, the suspension is printing under the UV light. So here is I have some models enabling functional design through DLP printing. So the CAD file we generate after the 3D printing we test, and after the some green body for mechanical properties and microstructure, and we have printing. So here I have using a DLP printing, I have printing some complex shape. As mentioned before, we can check the shrinkage and the physical property of the material by printing three direction, x-axis, y-axis, and the z-axis. And the centering we find along the z-axis printing, the shrinkage rate is high. And the some complex shape, gyroid structure, diamond structure, and showered structure, and green bodies. And this in the last is the dental implant by Euretia stabilized zirconia I have printed. So here we are setting the debinding and the sintering temperature. Debinding oftenly we are up to 500 to remove of the organic under airs, and then we are using a sintering by different low sintering temperature level 15 to 50 by holding the times. So after we do characterization to measure the density measured by Archimedes method, microstructure using SEM, EDX, phase analysis, hardness, and Bexel. So here is the density of three composition I have printed: alumina, 3YTZP, zirconia, and kaolin, and I obtained the maximum density of this sintering 94% on 1550. After the 3YTZP 1550 93, and kaolin ceramic also 93 point. So here is the XRD result after sintering high low 1150 to 1500. They have no any phase change here. So here is the microstructure. You have picture 1150 to 1550. You will see here. So there is the solid content after the high temperature, the porosity reduced, and here also EDX maps you can see. So here is the sintered analysis of alumina of different temperature. They are facing interlayer spacing, interlayer and pores and connected borders, and they have. So here is the fractographic analysis to observe the cluster and texture of the grains. So after sintering high temperature 1670, I have got the viscose high density is 97.19. Here is after 1660 also we found there is no any phase change, and also here is the shrinkage rate. So here is the flexural strength and fracture toughness of the specimen of different. So 62% the fracture tough 3.84, and with the add of zirconia, the fracture toughness enhanced to 5.2, and here is the alumina reinforced zirconia specimen sintered at with the holding 2 times. So here you can see, for example, the span distance, the flexural strength is increased. So here are some complex shapes of my university monogram I have printed to ensure the precision and accuracy of the 3D printing. So here is the grain size of the zirconia ceramics 3YTZB. So here is the centered analysis of 3YTZ SEM EDX. You will see the how dense of the parts of the microstructure of centering high temperatures. So also here, SCM microstructure shows the connector borders, pores, unconnected borders, and some little pores. So the mechanical properties I have tested: hardness, modulus, Young modulus, and the linear fit. So after I observed the surface roughness of the specimen and significance enhanced flexural strength of the 3YTZ zirconia. So here is the summary and conclusion of my talk. So the current reinforcement strategies, critical problems such as the low density manufacturing solved by lithography. So influence of the sintering temperature, low temperature, high strength in XY direction. Strength depends strongly on the testing direction, and height similar strength in all printing. So then I correlation with printing direction and testing direction, and Taylor employed for the first time to strength of 3D printed ceramics. The layer upon layer deposition produce low combination of different material and generation residue, high degree and quality of texture with control debinding. So also the last slide, summary and conclusion. I have used the homemade resin was prepared. So printable suspension approximately for a case of alumina, I have used 62% volume alumina, and for Euretia stabilized 43% volume ceramic, and alumina reinforced solid content was the maximum 50% volume. Then the light parameters and slight thickness was adapted to composition of the suspension, and the binding and sintering cycle strategy was adopted to enhance the mechanical properties, application of the optimized parameter and complex shape, and parts printed with maximum 94% relative density with interesting for biological application and highest bending strengthening of achieve this one zirconia. So thank you for the, so this was my,
That, that's a wonderful presentation by Dr. Irfan Hussain. Does anyone have any query? Hope there are no hope there are no queries. And again, that's a wonderful presentation by Dr. Irfan Hussain.
thank you.
Let's move forward. Yeah, thank you. Let's move forward with the further presentations. The next presentation is by Dr. Seong Woong Woo, Ethiopia Technical University, Ethiopia. Hello, Dr. Seong. Hello, Dr. Seong.
Okay. Hello.
Hello, Dr. Seong Woong. Are you ready with your presentation?
Yes, I'm ready.
Yeah. Okay. So I'm making you as a presenter.
And can you activate
Yeah,
the
I
share
made you as the
ownership?
pres. Yeah, I made you as a presenter. Please share your screen. Click on the share option. Yeah, your screen is visible.
Yeah, yes, but the where is the PowerPoint?
Kindly open your PPT.
Yeah, yeah, yeah. Can you visible? Can you visible?
Yeah, it's visible. Please make it. Yeah, it's perfect. Continue with your presentation.
Yeah, I will start. Thank you for your listen to my presentation. My name is Dr. Gu. Today I briefly introduce of the U-derived methodology. I will present entitled as improving particle design of mechanical systems such as refrigerator. This methodology will be improved design of the mechanical system. This is the mechanical system. There are two of the mechanical system. One is a heat engine. Another one is a refrigerator. Heat engine is a produce work and from the hot and the cold. There are some the automobile and the airplane. Another one is the refrigerator. Refrigerator is a decreased temperature from the low and the higher. Uh, this is the automobile. Automobile is a consist of the engine, transmission, and driving, etc. Total component 20,000 pieces. Life targets between like 10 years. To improve the performance and the reducing cost, the product will be designed yearly. By reliable testing, engineers should be find design fault of the product. This is an airplane. Airplane consists of the machine and door, aviation control, etc. Total component 200,000 pieces. Life target between like 10 years. This is a refrigerator. Refrigerator consists of the cabinet, a door, internal fix, and etc. Total components are 2,000 pieces. Life target is between like 10 years. This is a definition of the reliability. Reliability is defined as ability item to perform the required function under the state and the environment operation condition to specific period of time. Most of the mechanical systems reliability can describe as bathtub. If I follow the desktops, the product will be rejected from the marketplace because of the initial failure rate, higher failure rate, short lifetime. Because of that, the company set up the left growth plan, and as design is improved, the bathtub will change to the straight line. Product reliability can be achieved and without design failure. This is a sinking picture of the RS Titanic in 1912. It came from the cold seawater, brittle steel, and the temperature. Stop the side and the Titanic and stop the iceberg. As a result, the Titanic is 2,000 people on board. It takes 2 hours and 40 minutes to sinking drown to death of the more than 1,500 people. This is just of the challenge. It came from the lucky booster seal with to lava. Brittle O-ring is winter weather. As this debacle occurred in 1986, all crew members lost their lives, and many American people suffering and low esteem because of this failure. This is a Calypso of the point present in 1967. It came from the metal, the fatigue, and the critical R bars due to the Lambda traffic load. December 15 and 1967, a silver bridge collapsed under the weight of the rush hour traffic, resulting death of the 46 people. This is a crash of the Highland Comet. It came from the first commercial jet. It can be a structural failure resulting from the commercial jet in airplane. As a result, and the problem starting in the suffering catastrophe in flight, and after years entering airline service, with the 3 comet lost within 12 months, highly public accident. This is a failure mechanism and the new design. This is a structure and structure subject to the repetitive load. There are some the design flaw. The structure will collapse each lifetime. The issue how to find the design flaw, the layer probability. The issue the live testing and the Excel live testing. This is a test material in product and the metal and polymer and the ceramic and the composite. This is the graphic study of the my abstract. First, and I will explain the quantum well model, and then the transporter phenomena. In the process, I will develop a time to failure model. And to develop the accelerate testing, I will the modeling end of the system, and then from the communication, and from the communication, I will developing of the time to failure model. Based on the time to failure model, I will developing an accelerate factor. Finally, I will carry out and the parameter with the sample size equation. In the process, I will find some design part of the mechanical system. This is a quantum L model, and this is Schrödinger equation, and this is a boundary condition. Based on the boundary condition, we can developing and the solution. This is a linear transport phenomena in mechanical system. J is a flux, X is a driving force, L is a transport coefficient. For example, fixed law diffusion. F is a material flux, and X is the diffusion the force, L is the diffusivity. I will give you one of the example of the diffusion phenomena, and this is a solid state diffusion impurity in silicon. It takes place and electromigration-induced voiding, buildup of the chlorine and traffic, electric and hold. This is a junction function, and if I apply the electric field, a junction function it will be distorted, and the void is to migrate on the left-hand side. J is based on the result, the junction function is the function of the sine hyperbolic and exponential. This is the junction function in the silicon, and if I take inverse, we can find of the general stress model. The issue how to simplify and the sine hyperbolic function. Sine hyperbolic is static and linear, and stress and exponential. Most of the test is carried out in medium effect. Time to failure is simplify and empower stress and the temperature. Finally, we can obtain of the Excel effect is depend on the ratio of the effect and the temperature difference. This is a multiple. Power is a multiple system. Power can be defined as the product of the effort and the flow. For example, a translation system is effort is force, flow is the velocity, and most of stress is came from the effort, and the Excel effect is depend on the ratio of the effort and the temperature difference. I will explain how to derive the sample size equation. Further, follow the variable distribution. Light function defined as a function of the shape parameter and the characteristic light. If I take logarithm, we can find the Vx light. The issue how to describe the characteristic light. Characteristic light depend on the chi-square function and the testing data. Finally, we can obtain Vx light is a function of the chi-square function and the logarithm function and the testing data. To derive the sample size equation from the approximation of the Vx lives, there are two approximations: chi-square approximation and another is a logarithm approximation. Compressed level and 60%, R is less than 4, chi-square function approaching and R plus 1. And the cumulative failure rate is less than 20%, and the logarithm function approaching and X. If I rearrange it, you can find the sample size equation. I will give you one of case of study and for my methodology. This is a refrigerator. This is a newly designed crankshaft and compressor. There are a lot of design port of the compressor. We don't know which parts. Compressor light type depend on pneumatic part. To find them, it requires a lifetime methodology. This is a parametric design schematic. Compressor is the design to the increasing pressure from and the low higher. We don't know how to use and the custom user condition and environment condition. Engine should be designed each part optimally. Lifetime methodology consists of step part and failure analysis return product, parameter alt design modification, finally checking and the product achieved life target. This is a compressor in vapor compression cycle. This is a vapor compression cycle. This is a pH diagram. This is a schematic diagram of the compressor. Compressor is operating by a slide crank mechanism. This is damaged product in field. We found a lot of wear on the surface of the crankshaft due to the lubrication problem in field. It came from improper design of the structure. To modify and we reproducing parameter data and collect them. This is a load analysis for the XLI testing. This is vapor compression cycle. This is a TS diagram. From the conservation of mass and capillary tube, energy balance and condenser evaporator, we can determine mass evaporator and temperature evaporator and the condenser. Finally, and the time to failure model is dependent on the pressure difference and the temperature. I will explain how to derive the XLA factor. And as I mentioned before, XLA factor depends on the ratio of the pressure difference and then the temperature difference. For worst of case, pressure difference is 1.1. For XLA testing, we increasing it at the pressure difference almost 2. XLA factor is 3.4. And for temperature, worst of case dome temperature 19. For XLF test, dome temperature 120. XLF factor is 1.4. Total XLF factor is 4.6. We are flying the duty cycle, we can search out the design failure. To the calculated mission cycle, a life target of the domestic compressor is beyond like 10 years. XLF factor is 4.6. Total sample size of domestic compressor is 100. Compressor life target for 10 years, almost 87,000 cycle. If there is no problem, 19,000 cycle, we can guarantee compressor life target beyond like 10 years. This is equipment used for the XLI testing. This is a test jigger. This is schematic diagram of the compressor. And we can proceed the parameter with the equipment. This is the result of the first parameter alt, compressor locked due to the lubrication, 7 and 10,000 cycle. This is a filter photo. This is the result of the first parameter alt. We finding a lot of wear on the surface of the crankshaft. By parameter alt, we can reproduce compressor failure in field. And we checked in the design of the compressor. We finding the three design problem. One is a low lubrication area, and then the low starting RPM, and then material problem. As action plan, we design of the crankshaft. We changing and the glue, we adding and the new glue, and the changing and some dimension, and changing and the material. By parameter alt, and we can collect the compressor failure. This is another result of the second parameter alt. Crankers were the founding 19,000 cycle. It came from the interference between the crankshaft / wall due to narrow clearance. This is the old design, and this is a new design. Ejection plan, we increase and the clearance from the 0.1, 0.5. By parameter alt, we can modify design port of the compressor. This is a summary of the parameter alt result. There is no problem 19,000 cycle. In first parameter, we founding and the duplication problem. In second alt, we founding and the wears on the surface of the crankshaft. In third alt, there is no problem 19 and 20,000 cycle. Compressor achieved life target beyond like 10 years. This is another case of the study hinge kit system. This is the refrigerator. This is hinge kit system. Hinge kit system is consists of several parts: cover, damp, and the spring and the housing. There are a lot of design parts of the hinge kit housing system. We don't know which part was. At the hinge kit system life target depend on the design flow of the part. To find them, it requires the reliable methodology. This is a parameter designer schematic. The integrated system is designed to close the door smoothly. We don't know how to use and the customer use and the loading condition and environment condition. Engineers should be designed each part optimally. Reliable methodology consists of three parts: compare failure analysis, return product, parameter alt design modification, finally checking and the life target achieved. This is damaged product in field. There are a lot of the crack on the hinge kit housing. It came from the primary structure. By the reproducing parameter alt, we can collect them. This is load analysis sheet for the XLI testing. Hinge kit system is depend on the door weight. To increasing the impact, we added additional weight on the end of the door weight. By controlling an impact, we can carry out the XLA testing. This is how to calculate of the XLA factor. XLA factor is depend on the ratio of the impact. Worst of case impact is 0.1. XLI impact almost 2.7. XLA factor is 6.3. We applying some duty cycle, we can search out design failure. This is how to calculate the mission cycle. Life target of the hinge kit system is beyond like 10 years. XLA factor is 6.3. Total sample size of hinge kit system is 6. Hinge kit life target is for 10 years, almost 36,000 cycle. There's no problem 41 mission cycle. We can guarantee lifetime target is hinge kit system beyond like 10 years. This is equipment used for the XLI testing. This is hinge kit system, and this is a refrigerator. This is a test jig and the controller. We can proceed the parameter art with the equipment. This is the result of the first parameter art. Hinge kit housing of the hinge kit system crack and the 7 and the 50,000 cycle. This is a filter photo. This is the result of the first parameter art. We finding a lot of the crack on the surface of the hinge kit housing. By parameter art, we can produce and design the flow of the hinge kit system. As action plan, we reinforce the fragile structure of the hinge kit housing system. We adding some rounding outside. We adding some rounding inside. We also give it to the reinforced leaf and the housing and the deck system. This is another result of first parameter art. We founding and leaked the old damp. It came from the primary ceiling structure. This is old design. This is new design. By parameter art, we can reproduce design port of the old damp. This is second parameter art result. Hinge kit housing and housing cover of the hinge kit system crack and 7 and 9,000 cycle. It came from the material problem. When operating in the damp spot and the strike hinge cover. Finally, and the fracture of the hinge cover. As action plan, and we modify material from the plastic to aluminum die casting. And by parameter, we can modify the fragile housing of the cover of the hinge kit system. This is summary of the parameter art result. There is no problem and the hinge kit system 41 at the mission cycle. First parameter we finding and the fracture of the housing, leakage of the old damp. In second art we finding and the fracture of the housing cover. In third art there is no problem and the 41 and the 74,000 cycle. This is another case of the parameter art. This is a draw system. This is a laboratory system. This is a newly designed and the draw system. There are a lot of the design part of the draws. We don't know which patterns. Laboratory light target depend on pragmatic part. To find them, it requires a lambda methodology. This is a parameter design of schematic. Draw system is a design the storing food. We don't know how to use and the custom use condition and the environment condition. Engineers should be designing each part optimally. Relative methodology consists of 3 parts: failure analysis, return product, parameter art design modification, and finally checking and the product achieve the right target. This is damaged product in field. We found a lot of damage the draws due to the design after use. It came from the improper design of the structure. To modify and we reproducing and by parameter art and collect them. This is a load analysis for the XLI testing. This is draw system. This is a pre-body diagram. And the draw box and the draw system is depend on the storing food. And by controlling and food weight, we can carry out XLI testing. This is the how to calculate the XLI factor. XLI factor is depend on the storing food ratio. For worst of case, food weight is almost 6. XLI testing and almost the food weight is almost 12. XLI factor is 4. And we applying at some duty cycle, we can search out the design failure. This is how to calculate the mission cycle. Life target of the draw system is beyond like 10 years. XLI factor is 4.0. Total sample size of the draw system is 6. And the draw life target is 14 years, almost 36,000 cycles. There is no problem. 34,000 cycles, we can guarantee the draw life target beyond like 10 years. This is equipment used for the XLI testing. This is art equipment. This is a controller. We can proceed the parameter with the equipment. This is the result of the accelerating loading in first parameter art. We founding and the support center is bent. Also is the low line is broken away. It came from the insufficient strength due to design flaw. By parameter art, we can reproducing and draw failure. As action plan, we design of the system for center support. We adding and two additional reinforced leaf. For guide rail, we excluding a dollar support. By parameter art, we can collect the draw failure. This is the result of the first parameter art. The box cover is broken and the 3000 cycle. This is the failure of the first parameter art. This is the result of the infielder crack. We found a lot of the fracture of the draw system. By parameter art, we can reproduce and draw failure in field. As action plan, and we checking and the design, and the fracture is came from the design defect in the low corner round in high stress interaction area. As action plan, we did the design of the box. We second and some the reinforced lead, and also applying and some the pillar in the intersection area. This is the second parameter art result. We founding and collect the guideline, and then also sunken roller and 6000 cycle. By parameter art, we can find a draw photo of the draw system. As action point, we design of the draw system for the support center, and we added in some the some added in some the lead, and for guide rail, and we added in some the backside lead, and we also increasing on the round and of the in the pillar. By parameter art, we can collect and draw failure. This is a summary of the parameter art result. There is no problem, and 30,000 cycle in first parameter we founding and Fox rail and design problem. In second art, we founding and supporting rail and design problem. In third art, there is no problem, and at the 20,000 cycle. Conclusion. This is my paper submit to the mechanical system and the signal process entitled as Improving the Lifetime of the Mechanical System during a transit establish and the quantum and the transport the life stress prototype and the sample size. This paper is explain the background of my design theory. This is my books and entitled as the Design of the Mechanical System. This experiment design methodology describes the new parameter art for the derived quantity testing and specification. It enabled to the mechanical civil engineer to find the design flaw of the achieve the target product reliability. It also suggests the private case of study on the mechanical system, present the Dakuchi method and alternative experimental methodology. This is my recent publication. Thank you. Thank you for your listen to my presentation.
That's a wonderful presentation by Dr. Seong Woo. Does anyone have any query? Hope there are no queries. Let's move forward with the further presentations. So the next presentation is by Dr. Mani Bharati from Chalapati Institute of Engineering and Technology, India. Hello, Dr. Mani Bharati. Are you ready with your presentation?
Yes, I'm ready with my presentation. Can I
Yeah.
share my
Yeah. Hello, Dr. Seong Woo. Can you please unshare your screen? Hello, Dr. Seong Woong. Can you please unshare your screen?
Hello? How to unshare?
Hello.
There is no option.
Please please unshare the screen.
Yeah, this is okay?
Yeah, yeah. That's yeah. Thank you. So, Dr. Bharati, I'm present now. Please click on the share.
Share is not highlighted, ma'am. Please make me as a presenter.
Please click on the share button.
Yeah, my share. Okay. Now my screen is visible, ma'am. Yes. Hello.
Yes, yes, it is. Yes, it is.
Um, hello everyone. Uh, I'm Dr. Mane Bharati, Assistant Professor at Shalpati Institute of Engineering and Technology, LAM, Guntur, India. My core research is special electrical machines and drives. So, thank you for giving this opportunity to present on advancements in 3D printing and additive manufacturing techniques through integration with finite element analysis. We all know that over the last 3 decades, research into the printing technology like additive manufacturing has progressed from fast prototypes to industrial level 4.0. So in the third 3.0 industrial revolution, that the main agenda is to minimize the cost, and you have to fast production and also low cost, and you have to give the most durable for every component in every industries. So the metal 3D printing is metal powder 3D printing is mostly used technology in the growing sector. The metal additive manufacturing is increasing day by day to utilize and to create the final products in many applications like automobiles, medical, robotics, uh, and also for renewables like wind generator systems and all. So the background main is additive manufacturing is the foundation of additive manufacturing is traced with Mr. Dr. Hideo Kodaba. He is but he is used for the 3D layers and 3D layers for the scanner 3D scanners and the layers technique they are used. Then the first additive manufacturing process can be developed Dr. Charles. But that process is that stereo lithography. This process is a very old process, but this process uh, will be using layer polymer resins can be used. There is a liquid polymers and UV lasers to build 3D objects by layer. This is having so many challenges, like it will be sensitive to the atmospheric and temperature because of layer, and because of the liquid. The and also it takes so much time to for the post processing stage, and it requires cleaning of the resins and excess resins. So SLA process is not suitable for the wind generator system and wind turbine generation system, wind blades and all. So selective layer sintering process. This process is used for the powdered materials, and use the UVA I mean UV laser type materials to sinter the materials, which will be used for the medical applications and the printers. In the last section given the refrigerators, so the complex and strong materials will be used to design used for the selective laser sintering type materials. And the classifications will be of mainly of 7, depends on the product and depends on the components we can use, we can adopt it. Most adopted techniques is the fused deposited modeling for the strong metal objects, and for the electron beam, and also DMLS and SLM. These four will be commonly used for the various commonly used applications in the industry. Actually, the mainly preferable wind turbine drivetrain mainly consists of wind turbine blades, gearbox, and the wind generator and converter and power grid. So we all discuss wind generator, gearbox, and wind generator design. So in the preferable, the materials are processing for the wind turbines is that wind turbines we can use epoxy type plastic type glass material can be used for the manufacturing. And also for the gearbox, for the materials like epoxy type materials for the wind blades. And the gearbox we can use as like alloys like copper, aluminum. We can use this steel laminated, we can use the gearbox type equipments. And for the wind generator, we can use the process like FDM process is mainly commonly used process for the wind generator modeling, and also used for the materials like steel. And for the winding we can use the copper and permanent magnets. So different types of components we can use different process for the different additive manufacturing process. Depends on the components and materials requirements and the structural demand. Based on the structural demand and based on the load requirements, we can use different type of processing to manufacture the wind turbine, gearbox, and wind generator components. This is the preferable additive manufacturing process for the wind turbine drivetrains. So the mainly workflow of the additive manufacturing process is two different processes there. For the simulation process is there, and additive manufacturing workflow. First we have to discuss about additive manufacturing simulation workflow. So in the simulation workflow, the first we have to start with the first we have to choose the objectives, and what are the parameters we have to upgrade it based on existing to the uh, based on improvement. So my challenge is that the wind generator design will be complex, and it will be very high, very weight, and we have to require the low cost. And these are the and also having main.
Hello, Dr. Sorry
Yes,
for interruption.
tell me, ma'am.
Yeah, your screen is not shared. Yeah, your screen is not shared. Can you please check that?
Yeah, sure. Ma'am, is this okay now? Hello, ma'am, is this okay?
Yeah, yeah, it's perfect. Yeah, it's
Okay.
perfect.
Yes. So the main challenge here is that wind generator in the working itself having some acoustic noise and some vibrations are there in the no load and load conditions of, especially for the wind generator which is having the permanent magnet structure. Now the technology of wind turbine system to extract the more power, we can use variable speed wind generator system. We can use for the variable speed, we can for existing we can use synchronous permanent magnet, synchronous generator. For the variable speed applications we are used. So the permanent magnet consisting of permanent magnets having some cogging torque issues. The cogging torque is nothing but the torque due to interaction between the permanent magnets and with the rotor. So permanent magnets with the rotor here, the red and green, like we can show that that is the permanent magnet. The above part is the stator and middle part is the rotor part. So it experiences some locking at the no load condition. It will be causes vibrations and some acoustic noise in the no load. So at the load condition, that will be the uh, function of the torque ripple. The load conditions also we can experience some vibrations and noise. The main agenda is to minimize the clogging torque issues in the no load and load conditions, and also maintain the all other electrical performances will be constant. That is the my main agenda, to minimize the clogging torque. So in the additive manufacturing simulation workflow consists of start program. We can start the design, we can start we using CAD design process. We can draw the simulation, we can draw the simulation, the 2D structure or 3D structure of a machine. So we can in the pre-processing stage we have to assign the materials, and also we have to assign the boundary condition. We have to choose the domain of simulation. Here for the generator sake I am choosing the domain have electromagnetic simulation I have chosen. We have to assign the parameters, like this is generator, we have assigned the parameters for the torque and all. We have to in the pre-processing stage we have to assign. So and we have to analyze the machine structure with respect to meshing technique is used. The meshing technique is used to analyze each component. The finite element is nothing but each component can be divided into small set of finite element. We have to analyze the finite elements, and we can take the polynomial expression for the each element. We can solve that complex problem into small problem. So this FEA is used. The based on FEA we can generate the mesh. The mesh is nothing but we can increase the accuracy of the mesh. We can use the small elements, we can get the more accuracy. So I am using the materials I have assigned for the machines, like for the lamination outer part I am using steel lamination. In the copper in the winding part I am using copper. So my rotor is a like salient type rotor I am taking for my wind generator to extract the more power. So for the simulation I have taken, for the meshing I have taken. If not meshing is not proper, our post processing and final product is not good. So my if I will move forward for the simulation of the mesh will be perfect, then only I can move for the post processing and final part. So the printing and post processing stage, in post processing stage in the simulation itself, the no load I will take the simulation results in the no load itself. After that I will go for the post processing stage to analyze the machine performances in the transient load conditions and steady state conditions. I can use the post processing phase and final part. After I choose in the post processing stage, and for the material properties and all will be validated, then only I can go for the additive manufacturing workflow. Then final test validation will be performed. So why finite element analysis? We have to be choose for electrical and mechanical simulation part. The For example, in for my simulation electrical magnetic circuit simulation, for the wind generator simulation of this wind generator accounting for the non-linearities in the magnetic circuit, it is performed by using a finite element analysis. Here the finite element analysis can be used based on the formulating the magnetic field problems in terms of magnetic vector potential. So the magnetic vector potential, the original problem can be subdivided into number of I think number of finite elements. That finite elements of the magnetic potential distribution within each element we have to be approximated with using polynomial expressions, and find the numerical solution for the field problems. Based on this I will get the magnetic vector potential of the edge. At edge it is a magnetic vector potential I am represented with the 2D. This solution can be obtained by the satisfaction of the boundary condition. I am taking the boundary conditions is magnetic field outside the generation is treated as a 0, and also vector potential, and A and J is the density of the vector having only in the axial direction. I have chosen because I am using only, I am simulated 2D dimensional only. Okay, this is the this is the 2D animation view of generator working. So I'm already said that the meshing is very useful tool to analyze 2D of the magnetic field problems. This The meshing technique is to dividing 2D region into a small set of triangular elements. Here we can see the triangular elements. We can analyze the vector potential at each triangular elements. This subdivision of the problem region is done using triangular elements of arbitrary shape, it having some arbitrary shape and size. The accuracy of FEA solution will be depends on the nature of the field and size of the element. The here For the increasing the high accuracy, I can take in 3 mm size mesh size and used for this model. We can get 1,000 elements I have analyzed. Here I already told that in the no load itself, having the generator having acoustic noise, and we can minimize the acoustic noise in the no load, and also we have to improve the torque tuning, means nothing but torque ripple at the load conditions. So my pre-processing stage, my machine is working good. So then I have in the no load, I have calculated the cogging torque value of the locking is acoustic noise is experienced by my machine is 2.45 newtons peak to peak torque. I have experiences through this machine at no load condition. The Actually, the cogging torque is can be calculated by using mainly Maxwell stress center method or co-energy method. What is meant by the cogging torque is nothing but rate of change of co-energy with respect to rotor displacement is nothing but cogging torque. The magnetic flux density can be calculated with respect to the permeance in the air gap, and also for MMF excited with the permanent magnets. Cogging torque for the simulation, the cogging torque can be calculated with respect to peak to peak torque under no load to the average torque under load. We can calculate the cogging torque. At no load, at load condition, the cogging torque is a function of the load torque. At load condition, the torque ripple is a function of cogging torque. I am developed the skewing technique. What is the skewing technique is nothing but the skewed rotor. We have to rotor can be sliced into number of subsections. The skewed rotor can be considered as a series of that will be the series of axial straight subtract displayed properly, that will be displayed in the properly. In this way, 2D FEA can be used. This skewing technique already developed for the induction motor to minimize the cogging torque. Here I developed for the rotor having the permanent stator having the permanent magnet structure, like I am designed with flux reversal generator. I am applied for this skew technique. So if the rotor is skewed to a certain degrees, the shift on the CT of each subtract will be superimposed on each other. The total CT will be minimized with the average can be smoothed out. So I analyzed the trial and error method for 5, 10, 15, 20 degrees for each subtract. So here FEA seems that the cogging torque will be minimized at 15 degrees, 0.1495%. It will be that will be theoretically agrees with theoretically also. The 15 degrees skew one is effectively minimize the cogging torque at no load condition. It will be decreased 92.2% of its average value. But these method having some reduction in the flux linkages and induced EMF, corresponding reduction of the power density in the no load. I am especially telling the no load. So the torque ripple is nothing but in the load condition. The torque ripple is minimized in the load condition. So in the torque ripple can be minimized by skewing technique, which is having 71%, but average torque will be minimum of 13% reduction is shown. The torque ripple is also minimized by using this skew technique based on these waveforms. So the main my agenda uh, is to adopt the finite element analysis before we can go for the additive manufacturing process, so we can minimize the acoustic noise in the no load and load conditions by using the skew technique. The technique is used to minimize the uh, minimize the I think highest percentage reduction of the cogging torque at no load, and torque ripple at the load condition. The but the average torque is little bit suffer. 13% will be reduction will be experienced by using this technique. uh, Thank you. Hello.
Thank you, Dr. Mani Bharati. That's a wonderful presentation. Does anyone have any query? Hope there are no queries. Let's move forward with the further presentations. So, he- hello, Dr. Mani Bharati. Can you please unshare your screen?
Yeah, sure.
Yeah,
Yeah.
thank you. So the next presentation is by Dr. R. Tiruchelvi from Amen Aqua Biochemical Free Plant Activator Manufacturer, India. Hello, Dr. Tiruchelvi. Are you ready with your presentation?
Yes, ma'am, I'm ready. Yeah.
Yeah. So I'm gonna make you as a presenter. Please click on the share button, please.
Sure, ma'am. Yeah.
Yeah, your screen is visible. Please make it a full screen and start
Yeah,
your
that's
presentation.
yes, ma'am. That's what I'm trying. Slide. Ma'am, is my presentation is available? I'm just trying to make us a full screen.
Yeah, your presentation, yeah, your screen is available, but it's not a full screen.
Yeah, that's why, ma'am. I'm trying, but I couldn't able to make it out here.
Yeah, click on an icon below. There'll be an icon at the right corner,
Okay.
bottom right corner. There'll be an icon for the full screen.
Yes, ma'am. That's what I'm trying, but it is not working out. And the slide is also not changing, ma'am. Yeah. One second. Yeah. One second, ma'am. Yeah. Ma'am, can you help me, ma'am? I'm just sharing it, but I couldn't able to access the next slide and make it as a slideshow.
Okay, can you please share your PPT to our program manager so that we'll be playing the PPT from our end, and you can explain that.
Sure, ma'am. How can I share it now?
Yeah, you can share it through mail or WhatsApp. You can do.
Okay, one
Yeah,
second.
please. Yeah, do that,
Sh-
and we will share from our end.
Okay, ma'am, one second. Mail means the mail ID which I got it, right?
Hello.
Yeah, ma'am, I'm sharing through mail. Yeah.
Presentation of syntax.
Oh, sorry.
Hello. Hello, Dr.
Yes, ma'am.
Tirushalvi. Yeah, can you
Yes,
try
ma'am.
it again? We'll check it once, and then if it, I mean, this is not possible, then we'll share it from our end.
Sure, ma'am. I will try it now.
Yeah,
Yeah.
yeah, I'm making you as a presenter. Yeah, I made you.
Yeah. One second.
Say again. In task, we go to pop-up window. In that, we have application and task. That can be shared in task. You'll get a pop-up. Kindly click on share button. You'll get a pop-up. In that, you will have share application on task counts. Run task and share. Characterization మళ్ళీ అప్లికేషన్ చేసేసింది ఇలా కరెక్ట్ చేసింది చెప్పు click on it.
Hello, hello, Dr.
Hello.
Tirushalvi.
Yeah, ma'am.
Yeah,
I'm sharing the screen again. I'm getting the same problem. Yeah.
yeah, yeah. Please unshare your screen. I'll again make you as a presenter, and then I'll instruct you, and you can follow that.
Sure, ma'am. Sure.
Already presented. Already she done shared. Now click on share button on screen.
Hello.
Yes, ma'am.
Yeah, click on the share button now.
Okay. Share screen. Yeah, ma'am.
So you'll get a pop-up window and select the entire screen.
Screen is coming, ma'am. Entire
No, no,
screen.
no.
Yeah.
Yeah, you have to select entire screen.
Okay, ma'am.
Yeah, now you open the PPT now.
Yeah, ma'am. PPT is already open in the desktop.
Yeah, please open that. Click on that. Yeah, now make it a full screen.
Now it is okay, ma'am.
Yeah, make it a full screen. Yeah, it's perfect.
Now it
You
is
can
okay.
continue
Shall
with
I
your
start,
present.
ma'am?
Yeah, it's perfect. You can continue with your presentation.
Okay. Thank you, ma'am. Yeah.
Thank you.
So, good evening to all. Thank you for giving me the opportunity to present here. So, my topic is on 3D bioprinted organ on chips. So these are the topics which I'm going to discuss today. So coming to the introductions, as we all know, nowadays the therapeutical practices, they are having the many kinds of medical trials. Mostly before and all, they tried it in animal models, for example mice or static two-dimensional cell culture phantoms. So the main difficulty in 2D cultures they are facing are insufficiently mimicking in vivo conditions of certain diseases. So coming to the to replace that 2D cultures into the 3D cultures, it cannot be replicate the dynamic microenvironment of the human body, such as biofluid flow. That means the blood and the lymphatic fluid of waste removal, nutrition supply, and drug transport, and some of the oxygen distributions and the mechanical stress experienced by the cells during the respirations and heartbeat. So overall, in order to mimic that disadvantages of the 2D and 3D cultures, and also using the animal models, so the most advanced method now we are focusing on is the organ on chip. Shortly we can represent as a OCC system, so which may be act as a convenient versatile means for mimicking the functions of different organs of our human body. So in future it is expected that 3D bioprinting market for medical and both health sectors will increase at a CG or a 14.5%, so which can turn up revenue up to 4.4 billions in 2028. And So this is about the overall of the organ and chip systems. So first what we are doing here is we are isolating the cells from the patient's different organs. It may be a brain, lung, gut, renal system, or bone or cartilage, skin, liver, breast, heart, and vascular systems. So next what we are doing is we are preparing the bio ink, and after that followed by the fabrication of the organ on chips with 3D bioprinting. So coming to the next step is that we are testing the target treatment on the organ on chip setups, and then we are applying for the clinical treatment to the patient. So this is all about the overall view of the organ and chip systems. And coming to the fabrication part, so there are generally four types of fabrications are available for the bioprinting. So they are the extrusion based, inkjet bioprinting, light enabled methods, and laser based 3D bioprinting. So extrusion based, we are using the pneumatic pressures or mechanical force which is generated by the piston or the screw type. And in the inkjet based method, we are using the nozzle or inkjet heads and the actuation mechanism. So here there may be a thermal, physioelectric, or electrostatic mechanism may be the reason. And coming to the light enabled methods, here they are using the photosensitive bio ink which is exposed to the light of the specific wavelength, so to polymerize or depolymerize. Coming to the last one is a laser based 3D bioprinting. So here we are using the cell laden bio inks by using the laser energy. So these are the basic types of fabrication methods which is available for the 3D bioprinting. And coming to the bio ink, so it may be derived from the natural sources such as alginate, which is also termed as algin or alginic acid, or carrageenan, or gellan gum, agar. It is also known as the agarose, collagen, fibrin, gelatin, silk, fibrinogen, and methyl cellulose, and hyaluronum. So there may be some synthetically bio ink may be derived. So they may be termed as a polyoxomer, matrigel, poly-PCl, and PEG, polyethylene glycol, gel MA, polyvinyl alcohol, polylactic acid, and PLGA. So the bio ink which is used in the 3D bioprinting are maybe generally classified into two groups. So they are the cell scaffold based approach and the scaffold free cell based approach. Cell scaffold based approach means it is a bio ink which contains the biodegradable material and the living cells. So and after bio imprinting the process, the biodegradation begins and the cells grow to occupy the vacant space. And coming to the second method, that is scaffold free cell based approach. Here the bioprints, we are imprinting the bio cells, living cells directly in a manner which is similar to the normal embryonic growth. So these are the generally two main categories of 3D bioprinting bio inks which we are used here. And coming to the cell source, so what are the cell source that maybe we can choose for this kind of OCC systems are stem cells, primary cells, and immortal cells. As we all know, stem cells, it have the ability to become the various types of cell types from heart muscles to brain cells. So the main type of adult stem cells we are using here is hematopoietic stem cells, MSC, neural stem cells, epithelial stem cells, and skin stem cells. Coming to the primary cells, so here the cells are isolated directly from the living organs or tissues, and they are using immediately. These kind of primary cells they are using in the chip platforms for kidney, liver, neurovascular units, lung, heart, as well as drug resistant testing and drug delivery studies. Coming to the immortal cells, here the cell culture systems with the ability to replicate indefinitely in a repeated process. So these are the three types of cell sources which we are used in the OCC platforms. Coming to the next, so next we are going to see about some of the biomedical applications of the 3D bioprinted OCC platforms. And so first we are going to see about the brain and the BBB, blood-brain barrier. So among the various types of diseases which we are seeing in our brain, so the most important thing is the glioblastoma. We can name it as a GPM, which is a grade 4 astrocytoma. So which is a rapidly growing and aggressive brain tumor. So this we can achieve by using the XYO GPM on a chip models. So here this picture explains how we have done a chip on models. So to bioimprint an XYO platform, first we are using the glass substrate, so followed by the silicon ink to be print on the chamfer wall. Next the GPM cells as well as the vascular cells which may be embedded into the brain decellularized ECM, that is extracellular matrix. Then this BDECM or the collagen cell which may be tested for to determine the patient specific therapy resistance and to investigate the drug combinations for a more effective tumor killing performance of treatments. So this is the OCC system for the GPM grade 4 astrocytoma. And next is the lung and the airway. So here many respiratory disorders are there, but the most peculiar one to target for this OCC to design the OCC platform is allergen induced, which may be asthma, exacerbations, and asthmatic airway inflammation. So these may be considered as a severe respiratory disorders. So here we are doing the 3D vascularized airway on a chip. So the thing is the fabrication process of vascularized airway on a chip. The first picture explained. So we are isolating the natural ECM microenvironment, and we are incorporating with the cell laden based ECM bioinks, and then we are imprinting on the 3D printed vascular platforms. And the second picture, which clearly explains that this vascular network formations of the 3D cell bio printed vascular platform. So this picture clearly explains this vascularized airway on a chip, so which may be mimic the our respiratory process. And the third image, it can clearly explain about the scan imaging, that how it can mimic the airway on a chip. So this is about lung and airway. And coming to the next is the liver. So as we all know, liver, there are many untargeted diseases out there. So here they are focusing on the hep G2 or C3A periods for the drug toxicity. So in the picture A, they are doing the fabrication process of the proposed platform with simultaneously bioprinting the different cell types using three nozzles. Here three nozzles are there. First in the cell type A, cell type B, and cell type C. So they are imprinting with the hydrogel B. So this is the on the down, it is organ on chip platform. So this is the printing of the channel cover. Here the tube connection part is there. So they are imprinting by using the PCL printing for microfluidic channel. And the B picture, which can clearly explain the side and the vertical view of the liver on chip platform with developed perfusion system. Here the endothelial cells are there. This is the inlet and this is the outlet. So inside that the fluidic channels is there. So they are given the size of 1.1 mm and 400 micrometer. And the third picture, which can clearly explain the transparency of the PCL based channels, which is on the top, which is compared with the polydimethyl siloxane, that is PDMS based channel thing. So on the fourth picture, it can give the overall outline about here the peristaltic pump, which is used on this liver on chip, and the outlet in the reservoir is getting collected. So this fluidic channel has to have the thickness of 1.5 mm thickness. So this is for the liver OCC system. And coming to the renal OCC system, so the most targeted, this is for construction of this OCC for renal systems are chronic kidney disease. Shortly we can tell it as a CKD. So what is CKD means? It refers to the malfunction of the kidney in the filtering of blood, so which may be result in the kidney failure, heart disease, anemia, infections, low calcium, high potassium, and high phosphorus levels in the blood. So nowadays the most effective treatment for kidney disease is needed, since 5.24 billion people require dialysis by 2030. So here the kidney on chip platforms, what they are doing is the 3D bioprinting technology can produce some complex luminal tissue architecture. So that is the challenging part, that is the advantageous part. So we are constructing the vascularized human proximal tubule on a chip, which is some complex structures in the kidney, so which may be used to study the CKD. This is in a OCC platforms. So here in this picture, they are trying to sequentially bioprinting the steps to fabricate the kidney on the chip model. So they are using the pluronic ink and gelbrain ECM. So they are printing that. After that, followed by the casting and evacuating the excess ink, and then they are adding the cells and done in the perfusion method. And the next picture, it clearly explains the coupling the OCC, that is organ on chip platform, which is close to the loop perfusion system for the quantitative measurements of the renal reabsorption. Because the main advantages why we are going for this CKD, this is in the OCC, is so the construction of vascularized human proximal tubule is a challenging task in other 2D or 3D cell culture. So this system provides one of the main advantages for studying this human vascularized proximal tubule on a chip. So this is about the renal system, and followed by the breast. So as we all know, among the various types of cancer, the breast cancer is commonly diagnosed in the woman, which may be increased by 0.3% per year. So in order to sort out that issues in the OCC, with the help of the OCC, we are diagnosing the 3D tumor array chip, that is 3D TAP, which may be bioimprinted with gel MA hydrogel droplets, which contain the MDA MB231 breast cancer tumor cells, which can be evaluated with the epirubicin as well as also paclitaxel anti-tumor drugs to demonstrate the compatibility with the traditional screening approaches. So here the tumor on chip platform, which is imprinted on the microfluidic bioreactor with the dynamic environment, which consists of as well as both the blood and the lymphatic vessel pair, and MCF7 breast cancer cells, which may be imprinted on the 3D hydrogel matrix based gel MA on a PDMS and PMMA frame. So this is about the picture of tumor on chip platform with blood and lymphatic vessel pair. Here the tumor in vivo we are taking. We are in the green color represents the tumor cells. So the tumor tissues, both the blood cells and lymphatic vessels are incorporating between the tumor tissues. And next one is the lymphatic. This is the OCC, that is organ on chip platform. So here we are perfusing that lymphatic train as well as the blood flow, both the things are incorporating. And this picture clearly explains the bioink composition, the lymphatic vessels within the blood vessels. So how we are alginate, gel MA or photo initiator, with the help of this we are doing that incorporations of the bioink. Followed by that we are doing the coaxial nozzle. So finally we are doing the perfusible and one end blinded 3D bioprinting, so for this microtumor. And next one is the so we have seen the different organs for the OCC platform. So the main advantage why we are going for this ultimate goal of this OCC platform is to produce the multi-organ platform to investigate the interactions of the different organs while monitoring the possible responses and negative side effects of administered medicine. So most of the current OCC platform, they are optimized for a specific organ. So previously we have seen for a targeted for a blood, renal system, liver or breast, we are targeted only for a specific organ. So another things are in a proof of concept design, that is a multi OCC platform which was developed using the DLP technology with separate compartments. So here what they are doing is they are doing it enable the culture of three different types of tissues on a single chip with the tissue specific perfusion rates to study the tissue tissue interactions through interconnective microfluidic channel. The channel radius may be 1 mm in diameter. And this method, that is proof of concept design, is based on the two fabrication method. One is with PDMS microfluidic core unit and another one is based on the 3D printed units, that is MOC, multi-organ chip. So here PDMS means they are using the polydimethyl siloxane. So what is the main use of this 3D printed unit means it is used to facilitate the culture of different cell types in different compartments which are connected by micro channel, which enabling the separated control perfusions. So we are, so this is the main advantages why we are in the OCC we have to see for the multi-organ platforms. So this is the PDMS based MOC disposable unit fabrication. So in the picture A they are using the CAD template. So this is the top template and this is the bottom template. So in the picture B they are incorporating the porous membrane deposition inside that design. And in the next picture, so it is the PDMS based chips. This is the PDMS ports, and inside that we are incorporating the PDS membrane, and then followed by that the template assembly and the PDMS coring is there. So this is based on PDMS based method for the multi-organ thing. In a single OCC, we can have the three different types of tissues, and we can study how it is getting responding. And second method, we have seen the whole 3D printing based MOC design. So here they are doing the MOC platform which can visualize the 3D printed parts. And in the second one, it have the 4 couple inlets and the outlet method. So while the ports are connecting the cell culture compartment, the remaining ports which enable the control perfusions of the fluid to each separate compartment. And in the third picture, we have see the 3 different colors, that is yellow, red and blue thing. So which are demonstrated in the unmixed flow, that is in each thing there should not be a mixture of the different kinds of things. So it unmixed flow there will be there. So this picture explains that. And in the last one, it is a cross section of the MOC which will have the 3 compartments for the cell seeding. A lower cell means which is a light blue color, and in the upper cells which may be a pink color. So this is about the whole 3D printed based MOC design. And coming to the challenges and concluding remarks, though they have the most advantages, we have to focus on some of the challenging things in the OCC platforms. So they are now we can replace the magnetic levitations. So in cell separation, isolation, characterization in microfluidic channels at the outlet of the chips, which can be enabled for analysis of the changes in the concentration of the elements in perfusion medium. And then another ultimate goal for OCC is the development of body on chip platforms, which enable the patient specific disease investigations and drug training considering all organs. So, however, the media which is used for the perfusions on OCC are usually optimized for a specific organ. So, we need to find out a single culture medium that is alternative for blood that is compatible with multiple or all organs would be an interesting area for research on the future. So we have seen all the organ on chip for different kinds of organs, and also the multi-organ, how we are targeting for three more tissues in a single OCC platform. So the current future research should be on OCC is so we have to focus on hepatitis B virus, that is HBV, so which is incurable and it can affect more than 257 billion people worldwide. So development of a cure has been slow because there is no model system to test the potential therapies. So by uncovering the virus intricate of evading the inbuilt immune response, the liver on chip platform provides the information that could be exploited for the future drug development. So here there may be many liver on platform for the hepatitis virus are there, but still not more researchers are there how to change the hepatitis B positive to negative, because most of the people without having any symptoms they are getting affected to this hepatitis B virus in India and all over the world. So we have to focus the research by using this OCC platform to for the targeting this hepatitis B virus. So that is future research on OCC. And thank you.
Thank you, Dr. Tirushalvi. That's a wonderful presentation. Does anyone have any query? Okay, hope there are no queries. Let's move forward with the further presentations. Thank you, Dr. Tirushalvi, once
Thank you, ma'am.
again. Thank
Yeah,
you.
thank you so much for this time.
Thank you. The next presentation is by Dr. Milan Marivan M. Amin and Dr. Naiwan Satrip Abdul Rahman from American University of Iraq, Suleiman, Iraq. Hello, Dr. Milan Marivan. Are you ready with your presentation? Hello, Dr. Milan. Are you ready with your presentation? Hello everyone. It takes approximately 5 minutes to Dr. Milan to join us. So let's wait for him for 5 minutes. device on the outer surfaces as well for different. Hello everyone, thank you for your patience. So Dr. Milan is not available today, so at the moment, um, let's end the session today. By this, we come to the end of day one webinar. I would like to thank all the attendees and participants of today's webinar. Hope you enjoyed the webinar and gain knowledge from the seniors, and request you to attend tomorrow's sessions too. If you have any queries, you can mail our program manager. Mm, they will they will guide you accordingly. Thank you everyone.